Hi guys, in today's lesson we're going to be talking about forces and we're going to be doing a quick recap of everything that we've been doing for the last sort of 2 to 3 weeks. So the first thing that we did was we started to name a few different forces. So the force that we're going to talk about first is weight. So that is something falling due to its mass and gravity. We've got air resistance, we've got friction, we've got drag, thrust, normal force, reaction force. We've got lots of different forces. But the most important thing about forces is realizing that it acts in a certain direction. So for example, if you think about weight, it's always acting downwards because it's being pulled towards the center of the earth. So we say that the direction is down. If you think about friction or air resistance, they generally go against the way that an object is moving. So if I have my pen and my hand, if I pull my pen across my hand towards you, okay, the frictional force is acting against it. It's acting towards me. It's acting against the range of motion. Now, weight is quite an important force, and we're talking about it a little bit in more detail than the others because weight is very different to mass. Now, mass is how much of there is of something, and we measure that in kilograms, and you can't confuse it with weight. Weight is the force that an object has due to its mass and gravitational field strength, and we measure this in newtons. On Earth, we say that the gravitational field strength is roughly 10. 10 will do for year 7. So if my laptop has a mass of 5 kilograms, that means there is 5 kilograms worth of particles on the inside of it. Now, that is being pulled down towards the center of the earth due to gravity. So we say it has a weight of 50 newtons. Now, if I took my laptop, let's say, to the moon, there's still 5 kilograms worth of particles in my laptop. My laptop is still made up of the same number of particles. So it still has a mass of 5 kilograms. However, when I go to the moon, because the moon is much smaller than the earth in mass, then therefore it has a smaller gravitational pull. The gravitational field strength is weaker. So therefore the weight is less because it is being pulled down to the center of the moon with less force. So it might only have a 20 Newton weight there, but still maintaining the 5 kilogram mass. Now, after we finished talking about different forces, we moved on to looking at force diagrams, what they were, what they represent. So the first thing that I'm going to draw for you now is a force diagram, and I'm going to do it for the example that I've just given you. I've got my laptop on a table. Now, as we all know, my drawing skills are not great. So I'm just going to put a box and I'm going to write the word laptop in it to indicate where my laptop is. And my table is a world-class drawing like this. So now what I need to do is I need to draw a force diagram, and that represents all of the forces that are acting on an object at a given time. And I'm going to go from the center of my object, and I'm going to go down, and I'm going to label it. So I'm going to put weight, and I'm going to give it a weight of 50 newtons because it has a mass of 5 kilograms. But now this is what I've drawn so far. But this isn't a complete force diagram because this is not the only force that is acting on it. If this was the only force that was acting on it, then we know from our balanced and unbalanced forces that something would happen. This laptop would break the table. It would be accelerating downwards. It would push straight through the table. So there must be a force acting in the opposing direction. And we're going to label that on now. So again, I'm going to draw it from the same point. I'm going to draw a circle in the middle so that you can see that point a little bit more clear. And the name of this force, I'm going to call it the reaction force. Now, some people call it normal force. That is completely fine. But I'm going to call it reaction force for today. And I'm going to give it a size. So if the weight of the laptop was 50 newtons, then the reaction force has to be 50 newtons because we've already established if the weight was the only force acting on it and it was pulling down with 50 newtons, the laptop would go through the table. Well, on the other hand, if the reaction force was bigger, let's say that the reaction force was 100 newtons, so it was bigger than the weight, then the laptop would all of a sudden start to rise up. And we know that's not going to happen. So that is how we draw force diagrams. That's one of the more basic options, but what about if something's moving? Let's say that we have a car, and I'm going to draw my car. It's a grade 9, I think, in art. No? Okay. So I'm now going to label all the forces that are acting there. I'm going to say that my car is parked and it's on my drive. So it's got weight, pulling it down, and let's give it a size of 10,000 newtons. Now my car, I know, is stationary, it's not moving, so therefore the forces that are acting down have to equal the forces that are acting up. So I'm going to call this one reaction force 2, and I'm going to give it the same sized arrow. And I'm also going to give it the same size force of 10,000 newtons. Now, my car isn't going forwards, it's not going backwards, so it probably doesn't have any horizontal forces acting on it. So this, right now, would be fine. But let's say that I'm in my car and I'm driving, I'm going 30 miles an hour, and I'm maintaining that speed. I'm staying at 30 miles per hour. I'm not accelerating, I'm not slowing down, I'm staying at the same speed. I know that the forces have to be balanced. But now, because I'm moving, there needs to be a forwards force and there needs to be a backwards force. So I need to come up with some names for those. So I'm going to say that my forwards force is thrust. And I'm going to give that a size of 10,000 newtons. And the reason why I've given it 10,000 newtons is because if you look at the size of my arrows, all of the arrows are roughly the same size. And we know that the size of the arrow indicates the size of the force. But this still isn't finished. This currently tells me that the force acting downwards is equal to the force acting upwards. So the car is staying steady, it's not going down, it's not going up. But currently, because I have 10,000 newtons acting going forward and I haven't got anything in the opposite direction, then that means that this car would be accelerating. So I still need to add on my fourth force. And it doesn't matter what we call it. You could call it air resistance, you could call it drag, you could call it friction, any of those are fine. But for example, for now, I'm just going to label it drag. And I'm going to give it a size of 10,000 newtons. And the reason why it has to be 10,000 newtons is I know that my car is not speeding up, it's not slowing down, so the horizontal ones must be balanced. So the thrust must equal the drive. Now, if I wanted to make my car travel a little bit faster, and let's say that I wanted to now start accelerating, I go from a 30 mile per hour zone to a 40 miles per hour zone, I need to put my foot on the accelerator. And doing so, that provides a larger forwards force. So my thrust might now become 15,000 newtons, as I've drawn on here. Now you can see that the thrust is bigger because it's the longest arrow, which means that the forwards force is clearly much bigger than the others. So if we compare the vertical components first, the weight and the reaction force, it's 10,000 down, 10,000 up. So therefore, the overall net force is 0. Now, if we look at the horizontal, we've got 15,000 newtons going forward, and we've got 10,000 newtons going in the opposite direction. So therefore, it is being propelled forward with a force of 5,000 newtons. So that means that my car is going to start to accelerate, it's going to speed up. The fact that the arrows are unbalanced shows me that there is an unbalanced force, which we know an unbalanced force means that there is either a change in direction, a change in speed, or a change in shape. Now let's say that all of a sudden I see something come in front of me and I crash into it. And now my thrust is 0 because I've come to a halt. So I now have no forwards force. Now you can see that the weight and the reaction force are still equal. So the car isn't going to go up, isn't going to go down. However, now there is a 10,000 Newton gap going the other direction, which means that the car is either going to change shape, size, or speed. Now the odds are it's going to change speed because it's going to be traveling from 40 miles per hour down to 0 miles per hour. And the odds are that it is also going to change the shape of the car. Now the car has something there to protect it. It has what we call a crumple zone. And at the front of the car here, it's made so that when it comes into contact with something, it crumples. That means that it starts to scrunch itself up. The reason why it does that is it increases the amount of time that you are in the collision for. And if you increase the amount of time that you're in a collision for, then you feel less of the force because the force is being spread out over a longer period of time. But we'll come to that when you start your GCSEs. The next thing that I want to talk about is friction, when it's useful and when it's not useful, because without friction, we wouldn't be able to cope with everyday life. So it is vital that we have friction. Let's say that you wanted to get out of bed, you wanted to go to school, you wanted to do anything, you need friction to be able to move so you can grip yourself, so you can get out of bed. Where do you think friction might not be useful then? You might not want to use friction if you are a snowboarder, if you are a skier, okay, somebody who needs less friction because they want to travel as fast as they possibly can. But now can you give me an example of, if we look at a bike, where does a bike need high friction and where does it need low friction? I'll let you pause the video and I'll let you think about this. A bike will need low friction between the gears. If you think about the chain that goes round a bike, it needs to go as slick as possible so it's not getting caught on things, so it can move as freely as possible so you don't have to pedal as hard. Where do you need high friction? Well, you need high friction between yourself and the seat so you don't fall off. You need it on your handlebars so that you don't let go. You need it on your seat. You also need it on your tyres. There are lots of places where you need lots of friction. The next thing that we're going to talk about is density. And we should have been doing an experiment to help us, but we didn't get around to it. So let's say that I wanted to work out the density of this box. Well, we said that density equals mass divided by volume. And if I wanted to find the mass of this box, all I would do is put it on some scales. If I wanted to work out the volume, then I would use a ruler and I would do the length times the width times the height. And I would do that using a ruler. Now that is very straightforward. But if I was to say to you that I wanted you to work out the area of something that is irregular, let's say this pen, okay? I can't do length times width times height because that's not how I'm going to find the volume of this. I could find the volume of this cuboid by doing length times width times height, but for this, I couldn't. Now, I'm going to tell you how you can do it. I'm going to tell you it due to how Archimedes found out. Archimedes is a scientist that a long time ago, he had a bath full of water and he was trying to work out his own volume. And he thought, if I get into the bath, all the water that falls out is going to be displaced, which means moved out of the bath because of my volume, the volume of my body. So all of the water that falls out of the bath must be equal to my volume. So how does that relate to this? Well, if I wanted to work out the volume of this, I could fill a can of water that has a spout and a hole. Think like a watering can, something similar to that. Now, if you fill the watering can up to the top, we call them a eureka can in science, all the way to the top, and you let the water flow through the spout, and then eventually it's going to come to the bottom. Then when you put your object in, it's going to displace some of the water. Now, you couldn't just use a normal watering can. So for us in science, we have a spout that comes down rather than going up. But I suppose if you cut the end off a watering can, then the water would still fall out at the same rate. So that would be fine, but you can't use it if the slant is going up. So how would you do it? You fill it with water, you fill it to the top of the spout, then you let the water come out, and then you would place the pen inside of the water, and you would catch the water that comes out using a measuring cylinder. Now, the reason why we use a measuring cylinder is because that gives us a unit for volume. So the amount of water that comes out when I put the pen in will be equal to the volume of the pen. So then I can use some scales to find the mass, and then I can do an equation for density equals mass divided by volume. It's pretty clever and it's very straightforward. Now, the last thing that we want to talk about is speed, and you can see my previous video for talking about distance time graphs, so I'm going to leave that one out for now. But what is speed? What does it tell us? Well, it tells us how fast something is moving. That's what most people will say. But it also tells us how far something gets in a certain period of time. Now, if you think of the equation for speed, it is speed equals distance divided by time. Now, distance is measured in meters and time is measured in seconds. So we've got speed equals distance, meters, divided by time, seconds. So we have meters per second. So if you think of Usain Bolt, if he ran 100 meters, I'll write it down for you. If he ran 100 meters, and it takes him 10 seconds to run it, I know he can run it faster, but for ease, we're going to go with 10 seconds. If he ran 100 meters in 10 seconds, we can work out his speed. So we do speed equals distance divided by time. So we have a distance of 100 meters divided by a time of 10 seconds. So 100 meters divided by 10 seconds, which means that he travels at 10 meters per second, which means that in every second, he has traveled a total distance of 10 meters. Now, if you have a tape measure, and you can go outside and you are able to do this, measure out the distance 10 meters. Have a look at how far Usain Bolt can actually run in 1 second. If you want an extra challenge, you can time yourself and see how far you can get in 1 second and see how close you can get. Let's see if you can get over halfway. Thank you for watching and hopefully you enjoyed this recap.